Hello, this is Steve Groven, and today's topic is Newton's laws of motion. Now, the thing about law, or the thing about the laws of physics that we forget, is that we are always subject to their consequences. To start my discussion, I'd like to introduce you to a man named Isaac Newton. Okay, so Isaac Newton lived from 1642 to 1727. He was a mathematician. He was into optics, physics, astronomy, and gravity. Back in 1667, he wrote the book entitled, the book named Mathematical Principles of Natural Philosophy, and included in this book were his laws on universal gravitation, Kepler's laws of planetary motion, and the three laws we're discussing today: the law of inertia, the law of constant acceleration, and the law of momentum. Now would be a good time to pause. Okay, so let's start out with the first law. An object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line, unless acted on by an unbalanced force. Okay, so let me restate that law. The law of inertia: an object stays in place or keeps moving in a straight line unless a force acts on it. Okay, now the thing about an object at rest, well, if there's an object at rest, then there is no force acting on it. Okay, let me get my pen here. Okay, so we could write a mathematical formula. Force is equal to 0, the net force. Like, for example, an apple sitting on top of a table, there is a force, the gravitational force, pulling the apple down, but there's also the force of the table pushing up on the apple. We'll discuss that a bit more later. Okay, so since we're calling this the first law, since the first law is the law of inertia, I'll get you a definition of inertia: the resistance of any physical object to any change in its state of motion. In other words, an object sitting on the table is going to stay sitting on that table unless you push it. Okay, like for example, the coffee cup on the table. If you push at the coffee cup on the table, then, well, of course, the motion is going to be resisted both by the friction on the table, but it's also going to be resisted by the force of the coffee cup. Okay, so what I'm saying here is that the coffee cup's mass is going to be related to the inertia. In fact, mass itself is the measure of inertia. Okay, so how many of you have been in a bumper car before? And if you have not, well, that's something that you should try sometime. Okay, so let's talk about bumper cars. Now, in order to get the bumper car moving in the first place, you need an unbalanced force. Okay, either the motor on the bumper car has to start running, or somebody has to hit you. Okay, now you are in the bumper car, and another bumper car strikes your bumper car. What's going to happen? Well, the main thing that is going to happen is the bumper car is going to be shoved backwards. But at the same time, while that bumper car is being shoved backwards, you who are sitting in the seat are being pushed forward. I mean, you've felt this before. If you're in a car, mom or dad or you hit the brakes, you are going to go forward. That's because that your momentum, or I'm sorry, your inertia is going to resist changing the motion. You are going at a constant speed, or you're sitting still. As soon as the car brakes, you're going to go forward because the tendency of your body is to keep going forward. Okay, so another bumper car hits you, changes the car's motion. The collision is going to change your car's motion, but not yours. You still want to go forward at the same velocity, but then if you're safety conscious like I am, and I hope you are going to be wearing your seatbelt. Therefore, the seatbelt is going to jerk you back, another unbalanced force pulling you backwards back into your seat and keeping you from going forward. Okay, so I made up a little demonstration of momentum. Let me pull that up. Okay, so, or not momentum. I made up a little demonstration of Newton's first law of inertia, and there's a little bit of Newton's second law of a constant acceleration in there too. Okay, here we go. Okay, now I want to do a little demonstration here of the law of inertia. The law of inertia states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless another force acts upon the object. Like, for example, in the case of my pool ball here, the force that's retarding its motion is friction. The friction of the table is stopping the ball from going on and on. So, for example, if there were no friction on the table, I could supposedly hit the ball and have it bank off each part of the table and never stop. But the friction on this table, and also the ball, is really small. Therefore, the friction is going to slow this ball a lot sooner than might otherwise happen if, for example, I was playing with a full-sized pool table. So there it is, quick demonstration of the law of inertia. Okay, so one thing that I did mention in there is that friction was retarding the motion of the ball. As the friction was stopping the ball's motion, well, that's an unbalanced force that slows it down. The other unbalanced force that would be acting on the ball, but this is not going to be as significant as the friction, would be the air resistance. Okay, so let's move on to Newton's second law of motion, the law of constant acceleration. So the second law states the acceleration of an object depends on the mass of the object and the amount of force applied. Okay, I'm going to take a moment here to take a look at that. I'm sorry, that should have been A-M-O-U-N-T. Any of you, if any of my students are watching the video right now, that is a really good quiz question. Which word did Mr. Groven spell wrong? Okay, so let's take a look at restating that law, also known as the law of constant acceleration. When a force acts on an object, the object will change direction or speed. Sorry, there's two words misspelled. That's amount and object. I'm fairly certain there are not two B's in there. Okay, so let's take a look at what that's talking about. First off, the second law is going to describe the motion of an object when unbalanced forces act on the object. So it's going to depend upon two major things. It's going to depend upon the mass of the object, and it is going to depend upon the force applied to the object. So how does this work? Now, if the mass of the object is really large, then the acceleration is going to be lower. In other words, well, let me read that. Acceleration increases as the mass decreases, and acceleration decreases as the mass increases. It's like the difference between a sport utility vehicle and a Volkswagen Beetle. The Volkswagen Beetle is going to be able to accelerate a lot faster than the sport utility vehicle because the Volkswagen Beetle is so much smaller. Also, it's going to take a lot less force to slow down that Beetle because it is so much smaller than the sport utility vehicle. Okay, but anybody who has been in a SUV knows that those engines are built strong. So the acceleration is also going to depend upon the force. As the force increases, the acceleration is going to increase. And as the force decreases, the acceleration is going to decrease. So whereas acceleration is inversely related to the mass, as mass goes up, acceleration goes down, and vice versa, acceleration is directly dependent upon the force, which brings us to the first of our formulas. Acceleration is equal to force divided by mass. Force goes up, acceleration goes up, mass goes up, acceleration goes down. This is actually related to another formula that I use force is equal to mass times acceleration. You'll notice all I did is I just I just multiplied both sides by the mass so that force was by itself. In fact, force is equal to mass times acceleration is the one that we normally use. Okay, so I've already shown you a billiards table, or a really small one. But what would be a way that you could probably increase the acceleration? Now, those of you who have watched my video on friction know that another way to increase that acceleration or make it go faster would be to decrease the friction. And what better way to decrease the friction in a system than by putting it on a cushion of air? I wish I had an air hockey table so I can do some demonstrations with that, but I'm afraid all I have is this picture. So just kind of think about that. The speed, the acceleration depends upon a lot of things, but mainly it's going to depend upon the mass of the object, and it's going to depend upon the force exerted on the object. If you can lessen or lower the force that is retarding that motion, like lower the friction force, then you can get a larger force involved. Okay, last law. Whoops, sorry about that. Okay, last law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. This is called the law of momentum. For every action, there is an equal and opposite reaction. Okay, so another way to put that is all forces act in pairs. All right, so let's take a look at that video that was going while I started the slide. Anybody who's seen this toy before knows this as Newton's balls. If you can see what's going on, the first ball is going down to hit the balls that are on what's happening here is a transfer of energy. The first ball is transferring all of its energy to the balls that were not moving, and instead of those balls moving, so in other words, what you're seeing here is inertia is keeping those three balls in place, but while the inertia is keeping those balls in place, all of the energy of the first ball is being transferred through all three of those balls to the fifth ball. Once the first ball hits the three balls that are in place, it knocks the fifth ball out of place just by transferring the energy. Okay, so let's talk a little bit about what is going on. What does it mean that all forces act in pairs? The pairs are the action and reaction forces. Anytime a force is exerted, there will always be a reaction force. Okay, and let me bring up another note here. The thing about the force pairs is they will not act on the same object. A force is always exerted by one object onto another. Just like in the Newton balls, the first object is exerting its force onto the second, and then the energy is being transferred through the second, third, fourth, right to the fifth. Okay, another thing that I'd like to mention about these action-reaction pairs is that the effect of the reaction is kind of difficult to see. Okay, now you know already that the acceleration of the planet Earth is, hold on, let me get up the pen. The acceleration of planet Earth, or anything falling to Earth, is 9.8 meters per second squared. So you know that anything that falls to Earth is going to fall at that particular acceleration. But what you probably don't know is that as the apple, like for example, if the apple falls from the tree, the Earth is pulling the apple towards itself, but at the same time, the apple is pulling the Earth up towards it. The thing is, while the apple is exactly exerting the force on the Earth, we really can't see that because the acceleration of the Earth towards the apple is so small, well, it's really not significant enough to see. But now that we've talked about the three laws, inertia, constant acceleration, and momentum, well, hopefully now you can see where some of the consequences are involved.